In this unit on gases, we learned two gas laws. The first was the combined gas law, and the second is the ideal gas law. And I think it's pretty helpful to understand the ideal gas law in the context of the combined gas law, or rather to compare them to each other. Remember that the combined gas law is a law that's used to calculate how pressure, volume, temperature, and moles of a gas may change between changing conditions. For example, if you have a gas, and that gas has a known pressure, volume, temperature, and number of moles, and then you heat that gas up, how do those properties change? And that's essentially what the combined gas law is used for. The ideal gas law, on the other hand, looks like this. There are a few things that I'd like you to notice right away about the ideal gas law. First is that a lot of the same variables are there: P, V, N, and T. There's an additional letter there in the ideal gas law, R. So the P corresponds to pressure, the V corresponds to volume, the N corresponds to the number of moles of a gas, or how many gas molecules there are. The T corresponds to temperature, and R is what we call the ideal gas constant. What we mean by constant is just that this value doesn't change. And we use the ideal gas law because it relates the pressure, volume, number of moles, and temperature of one gas sample. Meaning that if we know the pressure, the volume, the moles of gas, we can predict what temperature this gas is at. Similarly, if we know the temperature of a gas, how many gas molecules there are, and what the volume the gas occupies, we can determine its pressure. So for example, if you had a bicycle tire and you knew the volume of gas in that bicycle tire, you knew the temperature of the gas in that bicycle tire, and you knew the pressure of that bicycle tire, you could determine how many moles of gas were inside that bicycle tire. And so here's the ideal gas law again. And I mentioned something about R, that this R is an ideal gas constant. That value never changes. It's a value that relates pressure, volume, moles of gas, and temperature. It's what holds them all together. And the units that we're going to use for the ideal gas constant are liters times atmospheres over moles times Kelvin. Now that seems like a pretty crazy unit, but I'm going to rearrange the ideal gas equation here, and I hope it'll make a little bit more sense. I'm going to solve this gas equation for R. And now that I've solved it for R, go ahead and pay attention again to the units of the ideal gas constant. Liters is a unit of volume, atmospheres is a unit of pressure, moles, well, that's its own unit, and Kelvin is a unit of temperature. And those units in the ideal gas law match the units of volume, pressure, moles, and temperature. The unit of volume is liters, the unit of pressure is atmospheres, moles are just moles, and the unit for temperature is Kelvin. And those units are effectively the units of the ideal gas law. Back in our dimensional analysis unit, we determined that we could also cross out units in order to determine the units of our answer, whatever that may be. But here, no units cancel. So the ideal gas constant is a 4-part unit: liters, atmospheres, moles, and Kelvin. If you look up the ideal gas constant on Wikipedia, you'll see a list of about 25 different ideal gas constants, each with different values or units for volume, pressure, and temperature. And you see that the numbers change, but the relationship between volume, pressure, moles, and temperature doesn't change. The value just changes because those units and their scales are a little bit different. And I've mentioned a couple of times now that R is a constant, meaning its value doesn't change, and here it is. It's 0.0821 atmospheres times liters over moles times Kelvin. And that number is not going to change for us. It's a constant. In fact, it's not going to change for anybody. Now, on the previous slide, I said that if we knew the volume, the temperature, and the pressure of gas in a bicycle tire, we could figure out how many gas molecules there are in there. So, say for example, the volume of that bicycle tire is 0.78 liters. That it's a bright sunny day, and the temperature is 25 degrees Celsius, and you've just filled up your tires to the correct pressure, and that pressure is 6 atmospheres. Now we can use the ideal gas law to figure out how many moles of gas are in that bicycle tire. I'm going to write down the ideal gas equation first. And because we're solving for moles and we know that's what we're looking for, I'm going to solve the ideal gas equation for N first. And now that I've done that, I'm going to go ahead and plug in the values. My pressure is 6 atmospheres. My volume is 0.78 liters. And the product of those values is divided by the ideal gas constant R. And that ideal gas constant in the denominator is multiplied by temperature. And our temperature is 25 degrees Celsius. But remember, the units of our ideal gas constant R are liters, atmospheres, moles, and Kelvin, meaning the units of volume, pressure, moles, and temperature have to match these units in order for this relationship, the ideal gas law, to be true, and in order for us to use it. So the temperature in Celsius has to be converted to Kelvin first. And remember, Kelvin is Celsius plus 273. And so our temperature is 25 degrees Celsius. We add 273 to that, and we get 298 Kelvin. I'm going to go ahead and pop that into the equation up here on the right. And just like that, we can solve for N because we've put all of those values into the ideal gas equation. And when I plug that into my calculator, we get 0.19125 moles. And if we're using significant figures, that rounds to 0.2 moles. So just by knowing how big that bicycle tire is, its volume, what the temperature is, and what the pressure is inflated to, we've used the ideal gas law to tell us how many gas molecules are in there. And that's the utility of the ideal gas law. If you know 3 of those 4 variables in the ideal gas law, you can determine the 4th. And just remember that the ideal gas law is a law that's used to determine a variable under fixed conditions. Nothing's changing. Nothing was said about that this bicycle tire was then heated up to 50 degrees Celsius. No. None of the conditions changed. We just used the ideal gas law to find one of those variables.